Hello lovelies, in this video we're going to be looking at Group 7, the halogens. This is for your GCSE chemistry. Now, if you want some questions and flashcards to really make sure you understand everything behind this topic, then they're all waiting for you over on my website.
In this video, we're going to do a deep dive on the Group 7 halogens. The Group 7 start with fluorine, chlorine, bromine, iodine, and astatine. The Group 7 halogens are all non-metal elements that all have a common feature that they are poisonous or toxic. Because they're all in the same group, they all have 7 electrons on their outer shell. The Group 7 halogens are all what we call diatomic. This means that in their natural form, they will form pairs of atoms. During chemical reactions, all of the Group 7 halogens gain an electron in that reaction. And in doing this, they form -1 ions. So now let's look at some of the physical properties, looking at both their appearance and their characteristics. At room temperature, fluorine is a yellow gas. At room temperature, chlorine is a yellow-green gas, otherwise known as mustard gas. Bromine is a red-brown liquid. And iodine at room temperature is a grey solid. Fluorine is highly reactive and also, like all of the halogens, very poisonous. Chlorine is also reactive, but less so than fluorine, is also poisonous, but is a very dense gas. Bromine is a volatile liquid. That means it mixes easily with the air and is also very dense. Iodine is a crystalline solid, which means it has a crystal structure. It also undergoes sublimation, which is that process of moving from a solid directly to a gas, skipping the liquid phase. When it does this, it appears as a purple vapour. Now we're going to look more closely at some of the trends in these properties, how they change down the group. The melting and boiling point of the halogens increases as you move down the group. You can see this because the states change. They move from gases at the top to liquid and solid further down. This is quite easy to explain because as the atoms get larger as you move down the group, the intermolecular forces between molecules get stronger. This then means that more energy is required to overcome these intermolecular forces, making it harder for these molecules to change state. So this means that at room temperature, the physical states of these elements change as you move down the group, moving from gases to liquids to solids. Another noticeable physical property that changes is the colour of these elements. They actually get darker as you move down the group, starting with a yellow gas at fluorine to a grey solid at iodine. So now that we've described these trends, let's look at explaining the reactivity of the Group 7 halogens. The reactivity of the Group 7 halogens decreases as you go down the group. That means they get less reactive as you go down the group. As you go down the group, the number of shells increases by 1 each time. And halogens form -1 ions because they gain electrons during their reaction. As the number of shells increases as you move down the group, the distance increases between the positive nucleus and the negative outer electron. This means that the forces of attraction between that positive nucleus and that outer electron get weaker. That weaker force of attraction makes it more difficult for those atoms to attract that electron to their outer shell. This difficulty in attracting that extra electron is what causes the reactivity to decrease as you move down the group. The more shells, the weaker the attraction, the more difficult it is to gain that electron, the lower the reactivity. Let's look at the formation of metal halides. The Group 7 halogens react with some metals to form metal halide salts. The rate at which these reactions occur actually decreases as you move down the group. Given that we know that reactivity decreases as you move down the group, it makes sense that the rate of reaction between these halogens and their metals to form metal halide salts will also decrease as you go down the group. Halogens undergo something called displacement reactions, and we're going to look at those in a little more detail. A halogen displacement reaction occurs when a more reactive halogen displaces a less reactive halogen from an aqueous solution of its halide. Halide is an ion form of a halogen. So when we say from an aqueous solution of its halide, that means from an aqueous solution of a halogen that's already reacted with something to form a halide. Here we've got a table that shows halogens across the top and then their halides down the side. So this is potassium we've used here as an example, but this could be any halide that's formed. These three boxes that contain crosses show where the halogen and the halide are the same. This means that no reaction will take place because a halogen can't displace itself from a halide. Here we can see that bromine and iodine are showing no reaction when added to potassium chloride. Now, thinking about what we know about reactivity, that makes sense because bromine and iodine are both less reactive than chlorine, so are less reactive than chloride as its halide, so will not displace chloride from potassium chloride. When we add chlorine to potassium bromide, chlorine is more reactive than bromine, so it's more reactive than bromide, so a displacement reaction will occur. In terms of an observation, you will see a yellow-orange colour start to form, and that's the bromine that's been displaced from the potassium bromide. There will be no reaction when we add iodine to potassium bromide because iodine is less reactive than bromine, so therefore iodine cannot displace bromide. When we add chlorine to potassium iodide, we will see a displacement reaction. Chlorine is more reactive than iodine, therefore will displace iodide from potassium iodide. Here you would observe a brown colour forming, and this is the iodine being displaced. When we add bromine to potassium iodide, we will also see a displacement reaction because bromine is more reactive than iodine. In terms of an observation, you would again see a brown colour forming, and that's the iodine that's been displaced from the potassium iodide. When writing about the halogen displacement reactions, you may be asked to write ionic equations. Ionic equations are small equations that only include the ions that we're interested in looking at, so in this case, the halogens and the halides. For the reaction between chlorine and potassium bromide, the ionic equation would look like a diatomic molecule of chlorine, so that's two chlorine atoms bonded together, plus two bromide ions to give us a diatomic molecule of bromine and two chloride ions. This is because the chlorine has displaced the bromide from potassium bromide and has now formed potassium chloride, which involves chloride ions, and bromine has formed after it's been displaced. So of course there are no ionic equations for any reaction that's not going to happen, either because it's the same halogen with the same halide, or the halogen is less reactive than the halide. So for the reaction between chlorine and potassium iodide, you're expecting to see the same thing, except rather than bromide ions, you're going to have iodide ions. But again, you're going to form a diatomic iodine molecule and two chloride ions. You're going to see the same thing when bromine reacts with potassium iodide. The ionic equation is going to show a diatomic molecule of bromine, two iodide ions, forming a diatomic molecule of iodine and two bromide ions. It's really important that you can write the ionic equations for these displacement reactions, as it's something that comes up a lot. So alongside explaining what you would physically observe, as in the colour changes, you need to be able to write the ionic equations as well.
Ouch! This is why in some videos I have unexplained scratches.